PhD student at Imperial College of London. I'm going to present an active learning method for a Bayesian-adapted 3D hand pose estimation task. First, I'll go quickly through some problem definition and motivation, and I'll delve through our Bayesian adaptation proposal of the classic hand pose estimator together with a novel active learning framework. Finally, we'll go through the experiment section to conclude our hypothesis. Our main motivation in merging these two fields rely on high requirement of annotated data for deep learning models, especially in the 3D hand pose estimation, where an annotation process can take a lot of effort and it might still be imprecise. We have acknowledged that many of the current web-based datasets contain redundant samples. Therefore, we require active learning to bridge the gap between the learner's prediction capability and the data representativeness. As the active learning requires certain information from the model regarding the unlabeled data, we identified that there is no direct confidence metrics for regressions. Hence, we proposed a Bayesian adaptation for the 3D hand pose estimator, where distributions are approximated over the model's parameter. From this, we further derive the variances of the predicted posterior distribution. Finally, we include those uncertainties in our proposed sample. For simplicity, we deploy a standard deep prior architecture for 3D hand pose estimation. The objective function is defined as a mean square error, and as presented in Kendall et al., for the depth estimation task, we adapt a Bayesian approximation of deep prior through Monte Carlo dropout. Moreover, this also introduced in the loss function a variance that it is learned together with the model. We name this variance as a aleatoric uncertainty because it's learned together with the variance model. And mainly it balances out the noisy samples due to the acquisition or annotation process. The Bayesian deep prior introduced Drupal layers in the architecture, which are kept active during the inference or testing stage. Thus, this simulates the distribution over the parameter when the sample is inferenced multiple times. The resulted variance of the predicted skeleton is defined as epistemic uncertainty, where M is the number of Monte Carlo inferences. We denote that the epistemic uncertainty is strongly correlated with the model's learning confidence. This is a proposed pipeline where we have different locations of the Drupal layers that we test. The active learning framework is on a pool-based scenario, and we have a larger unlabeled pool of data, and at every selection stage we label batches with a defined budget, and the scope is of the active learning is to find the least amount of budget, the least amount of batches with the lowest or targeted loss value. Following the concepts from Corset, a geometric active learning method, we adapt and combine with the epistemic uncertainty from the Bayesian deep prior. Corset is based on the risk minimization between an initial training set and a Corset for selection. This is approximated through a key-center greedy algorithm. The figure represents this algorithm on the left and our variant on the right. First, we find the minimum pairwise distances between labeled and unlabeled predicted skeletons. Then from those minimums, we select the maximum distance, and finally we pick the corresponding unlabeled example. On CKE, we include in the distance computation the epistemic standard deviation. We consider three most popular 3D hand pose estimation benchmark, ICVL, NYU, and Big Hand. Before doing the active learning method, we analyze the Bayesian deep prior architecture, and we see that the dropout after every convolution layer is the best architecture, and we do Monte Carlo dropout only after 40 inferences. For Big Hand 2.2, we reduce the data set to make the test more flawlessly. When evaluating the active learning methods together with our proposed CKE, we consider the entire training set as unlabeled. From this, we initially randomly select a budget of 100 for ICVL and a budget of 1000 for Big Hand 2.2 and NYU. Before applying the active learning method, we create a random subset of 10% from the entire unlabeled pool. We further select through our proposed baselines under the same budget size. In this mode, we increase the exploration aspect from the datasets while avoiding the similar classes. For the first experiment, we compare the active learning baselines of random sampling and Corset when using deep prior against our proposed CKE for the Bayesian 3D hand pose estimator. We outperform these baselines on all datasets with large margin. The lowest trend is the better. We apply similarly the other methods on the Bayesian deep prior, and we also include an uncertainty sampling technique which picks the most uncertain samples from the unlabeled. We also analyze qualitatively the predicted hand skeletons at different stages. And we observe that CKE under the Bayesian deploy architecture produces the most accurate hand shapes even from early stages.